Welcome to Mile High Video Workshop 2020 and to my presentation titled Comparison Assessment of Emerging EVC and VVC Video Coding Standards with HEVC and AV1. This year, there were many significant developments in the video coding field, and the purpose of this talk is to provide you with technical observations to improve your orientation in this field and also to assist you in your decision-making process for selecting the right codec that answers your specific needs. The agenda is as follows. First, I will provide the motivation for the study, followed by a brief introduction into the VVC, EVC, and HEVC video coding standards, as well as the introduction into the AV1 codec. Then, I will overview the main technical features of the selected test candidates, followed by the detailed experimental results, which in turn will be provided for two AV1 configurations, one with a fixed QP structure and another one with a two-pass rate control. And at the end, I will outline the main key points of the talk by providing a brief summary and conclusions. The motivation for this study is actually straightforward. There are currently many different video codecs, and we need to clarify the comparative performance. So, what are the most deployed video codecs? This is of course AVC, which was approved 2003, and even after almost 20 years, it is the most deployed video codec. Then we have HEVC approved 2013, and its worldwide deployment is actually constantly increasing. We have H.262 MPEG-2, which is still mainly deployed in broadcasting. Now, regarding the codecs which have been developed outside standardization organizations, we have AV1 being developed by OM as substitution to video coding standards, and we have VP9 being mainly supported in the internet applications. Regarding the new video coding standards, we have VVC being developed by JEVIT, which was actually established as a joint effort between VCAC and MPEG organizations and finalized on July 1st, 2020, which is just several months ago. Then we have EVC and LCEVC being developed by MPEG only, while EVC was already finalized as well, and LCEVC is expected to be finalized quite soon. Now, regarding the VVC standard development process, the exploration phase of the video technology beyond HEVC started in October 2015 by established JEVIT as a joint effort between VCAC and MPEG organizations in October 2017. And officially, the VVC development started in April 2018 upon receiving responses to the call of proposals. And now, just about 2 years later, the first version of VVC is already finalized, which is very impressive. Let's discuss VVC main technical features. VVC has plenty of new technical tools compared to predecessors, including, for example, multi-type tree, according to which the coding tree block is first split into a quad-tree structure similar to HEVC, as you can see here in this figure, but then there are recursive binary and ternary splits, as shown in green and red lines in this figure, respectively. Then we have a reference picture assembling tool, resulting in enabling adaptive spatial resolution. We have a sub-picture concept, allowing a spatial random access. We have a cross-component linear model prediction that allows to decrease cross-component redundancy, according to which actually chroma samples are predicted based on the reconstructed luma samples within the same coding unit. And this is done by means of a linear model. In addition, for example, we have a wide angular intra-picture prediction modes of up to 85 directional modes. We have the affine motion compensated prediction applied on the block basis. This prediction actually based on the fact that in real world we have different type of motion, such as rotation, zoom, etc., and this tool appears to be quite efficient. We have an interesting tool which is called geometric partitioning, according to which a coding unit is split onto two parts by a geometrically located straight line. In addition, we have a combined inter and intra prediction tool. We have multiple transform selection tool for residual coding of both inter and intra coded blocks by employing multiple transforms, as can be seen from its name. Then we have an adaptive loop filter with block-based filter adaptation. While for the Luma component, actually one filter out of 25 is selected for each 4-on-4 block, based on the direction and the activity of local gradients. Further, we have an intra-block copy tool, which was already adopted in HEVC screen content coding extension, which actually is well known to significantly improve the screen content coding efficiency. So as you can see here, there are a lot of different tools which make the VVC video coding standard to be very comprehensive. Regarding EVC main technical features, so one of the important aspects about EVC that we have baseline and main profiles, while the baseline profile contains widely known tools which actually have been made public more than 20 years ago. In turn, the main profile contains additional tools with quite a significant coding gain. An additional important aspect is actually the fact that EVC design allows the most of the tools to be independently switched on and off according to each user requirements. And this is very important and very significant, I would say. Okay, so let's overview EVC main technical features. You can see a nice table here with overview of baseline in the main profile tools of EVC. And let's take a closer look specifically with regard to main profiles. It's more interesting. So, for example, here we have a tool so-called Split Unit Coding Order tool, SUCO. It's used for improving prediction by enabling a more flexible coding order. For example, from left to right, and in addition, from right to left. In order to, actually, it allows intra-picture prediction from the right reference pixels and also inter-picture prediction from the right motion vector predictors. It's quite a nice tool. In addition, we have here affine tool, okay, affine inter-picture prediction, providing 3 affine modes. One with 4 parameter model modes, another one with 6 parameter model modes, and the last one with the affine merge mode. In addition, we have adaptive motion vector resolution, AMVR, here, in order to reduce the bit overhead for signaling the motion vector information. Okay, we have MMVD tool here, which stands for merge with motion vector difference. This tool provides a new motion vector expression method. Okay, and it simplifies signaling by generating a candidate list, which is not being limited to the neighboring motion only. Right? And as a result, it removes much of the MVD signaling. And by such a way, the related indices are delivered to the decoder instead. Quite a nice tool. In addition, we have HMVP tool, which stands for history-based MVP. It allows to use motion vector information from the remote coding units. Here you have tool which is called ATS, Adaptive Transform Selection tool. We have here HTDF tool, which stands for Hadamard Transform Domain Filter tool. It allows to reduce ringing artifacts caused due to residual coefficient quantization. In addition, we have here DRA tool, which stands for Dynamic Range Adjustment for HDR. It's used for supporting more efficient coding of HDR and wide color gamut formats. Here we have Advanced Coefficient Coding tool. It uses zigzag scan with inverse order, including Chan transform coefficient processing and including bit plane context coding. So as you can see, quite many interesting tools we have here. Let's take a brief overview now of the HEVC standard development process. HEVC was developed by GCTVC, which was established by both VCAC and MPEG organizations in 2010, and the first version of HEVC was published in 2013. In turn, the second version of HEVC included range extensions as well as scalable and multi-view extensions, and it was published 1 year later, in 2014. Then, in 2015, the third version of HEVC was published, which included 3D video coding extensions, followed by the fourth version published in 2016, further including screen content coding extensions. Finally, in 2018 and 19, 3 more HEVC versions were published, mostly addressing additional ACI messages. And of course, we expect additional versions to be published in the following years. Let's discuss now HEVC main technical features. These features are currently well known and main features presented on this slide. So we have quad partitioning, of course, that introduced significant coding gain compared to AVC standard, which was based on the macro block approach. We have residual quadtree. We also have block merging that joins block of initial quadtree decomposition and creates a region of equal motion parameters. Quite a nice feature. We have advanced motion vector prediction, allowing to select two MVP candidates among spatial and temporal neighbors. We also have an angular intra-prediction with 33 modes. By the way, now it seems to be not a very significant number of directional modes, but in 2013 it was a very significant change compared to AVC. In addition, we have sample adaptive offset in-loop filter, which has a nonlinear amplitude mapping function, and Fuse applies individual mapping to samples based on the classification as H and non-H, and also according to the gradient orientation. In addition, we have parallel processing with styles and wavefronts, etc. So these are just main tools of HEVC. Let's discuss the AV1 codec, which is being developed by Alliance for Open Media, or in short OEM. The OEM was formed in 2015, just 2 years after the VP9 codec was finalized. The work on AV1 started from VP9, further adding additional tools on top of it, such as tools from VP10. The baseline version of AV1 was released in April 2016, followed by AV1 version 1.0 released in 2018. And recently, AV1 codec had a major update since 2018, and the second version of AV1 was released in May 2020 this year. Let's discuss now AV1 main technical features. And the features are as follows. We have a partition tree starting from 128 on 128 size block. You can see it here on the right side. We have enhanced directional intra-prediction with 56 directional intra-modes. Then we have a chroma from Luma prediction tool. We have an intra-block copy tool, which was already discussed earlier in this presentation. In addition, there is a warped motion compensation tool, including two affine prediction modes, which actually relate to global and local warped motion compensation. It should be noted that the global motion tool actually takes care of the camera motion, for example, and the local motion tool captures varying local motion. So it's quite interesting tool. There is a transform block partition tool, allowing Luma intercoding blocks to be partitioned into multiple size transform units. We have a constrained directional enhancement filter, which is actually a detail preserving the ringing filter, and it's being applied after the deblocking filter. And after estimating H in pattern directions, it applies a non-separable, non-linear, low-pass 5-on-5 directional filter. Further, we have a quite interesting tool which is called film grain synthesis tool. This tool is a normative post-processing tool being applied outside the coding loop. What it actually does, it removes the film grain from video content prior to compressing it, and then the film grain is synthesized at the decoder based on the parameters received from the encoder. And in turn, the synthesized grain is then added to the reconstructed video, and by such a way, quite nice coding gain is achieved. So this tool is, in my opinion, very interesting. Regarding the test candidates. Okay, so we have VTM reference encoder for VVC. We have ETM reference encoder for EVC, and we have HM reference encoder for HEVC. In addition, we have a AV1 version 2 encoder for AOM. Now, regarding the selected encoder configurations. So we selected the random access configuration since it provides larger coding gains compared, for example, to a low delay configuration. Now, the intra-period was set to 1 second. In addition, the rate control of VTM, ETM, and HM was disabled. Why? Because these are reference encoders which are single pass encoders, that substantially do not have a rate control mechanism. Of course, as the test conditions of these encoders have been aligned with the common test conditions used in the standardization process. Regarding AV1, AV1 was tested in two configurations. So first, with a fixed QP structure, and second, with the two-pass rate control in the VBR mode. Okay, now I will explain a little why there is a need to run AV1 in these two configurations. So AV1 is known not to perform well with the fixed QP structure encoding. You can also look at my previous works with this regard and the corresponding results. And the reason for that is quite simple. The reason is because AV1 doesn't have an efficient GOP hierarchical structure as video coding standards have. V1 is known as based on VP9 and the same thing was with VP9. So instead, AV1 actually mimics such a structure by employing so-called alt-ref frames. I'm writing it here, which can be coded with lower QPs. So each alt-ref frame, okay, can be composition of a future and past frames, somehow similar to well-known B frames. Okay. In addition, alt-ref frames are not displayed, and instead there is a skip mode can be used, and a regular frame which uses this alt-ref frames as the only reference is displayed. So as you can see, it's quite different from what we know from video coding standards. In addition, AV1 has so-called golden frames, okay? And AV1 can select the temporal distance of these golden frames in the past. By using both alt-ref golden frames in such a way, AV1 mimics the hierarchical structure of the video coding standards, and such a structure works much better when AV1 can significantly vary quantization parameters among alt-ref frames, golden frames, and the regular frames, okay, by using its quite sophisticated rate control mechanism. Okay, so to exploit the full potential of AV1 codec, we tested AV1 also in the two-pass VBR mode with the rate control enabled, allowing by such a way the AV1 encoder to increase its coding gain. Okay. Now you just should understand that such a comparison can be considered less fair for the reference software encoders because they do not have a rate control mechanism. Okay. Regarding the test methodology and evaluation setup. So in this slide, you can see a list of enabled tools of the VVC reference software encoder. Okay, the rate control is disabled as we already discussed, and you can see it here. Most of the tools are of course enabled in order to exploit the full potential of the VVC video coding standards. You can clearly see a main test settings in this table. This slide presents configuration settings of the EVC reference software encoder. You can clearly see on this slide which tools are enabled. Similarly to the tables that we had in the previous slide, the rate control is of course disabled, as we already discussed in details. And it's important to note that the configuration settings among all tested encoders have been aligned according to the common test conditions to provide a fair comparison. And similarly to previous slides, here you can see configuration settings of the HEVC encoder. Similarly, the rate control is disabled, and you can clearly see which tools have been enabled. Let's take a look at the AV1 configuration with the fixed QP structure. The GOP size was set to 16, you can see it here, and the intra-frame period was set to be similar to that of VTM, ETM, and HM reference software. Okay, so we actually align the settings with the reference software encoders. We also defined a small QP range. You can see it here. There is a difference between minimum and maximum QPs. Okay, why? In order to allow AV1 to vary a QP among its alt-ref, golden, and regular frames, and by such a way to allow AV1 to have a hierarchical structure similar to that of the reference software encoders, in order to allow a fairer comparison in this work. Let's take a look now at the V1 configuration in the VBR mode with the two-pass rate control enabled. Since the rate control is enabled, the quantization parameter can vary from 0 to 63, which is the maximum value. Therefore, in this configuration, a V1 encoder sets QP values to its ultra frames, golden frames, and also regular frames, which we discussed earlier in details, to whatever it decides is optimal for encoding. Similarly, the gop size was set to 16, and the intra-frame period was set to be the same as that of the reference software encoders. So all settings in this configuration have been aligned with the settings of the reference software encoders, including the target bitrate, which was set to match the bitrate of VTM, ETM, and HM reference software. And now we are coming to experimental results. Here you can see the evaluated video content based on VVC common test conditions. So the video content includes video sequences from varying resolutions. You have 10-bit 4K sequences, you have 10 and 8-bit 1080p sequences, you have a lot of 8-bit video content for lower resolutions, you have also class F that represents the screen content. So the content varies from different resolution, frame rates, bit depths, etc. And now we are coming to a more interesting part of this talk, the actual experimental results, which are presented in this work in terms of BDBR weighted PSNR YV values as indicated here. Let's take a look at this table in more details. As you can see, VVC outperforms HEVC by almost 40% in class A1, which are actually 4K sequences, and about 43% in class A2, which are 4K sequences as well. However, the computational complexity compared to that of HEVC is relatively high. In turn, EVC provides a coding gain of about 30% for encoding 4K video sequences, with the computational complexity increase varying between something like 3 times and 4.5 times compared to that of HEVC. So the computational complexity of EVC is actually twice lower than that of VVC. Okay, and I'm remind you that we are testing reference software encoders. On the other hand, let's take a look at the AV1 coding gain. So AV1 with a fixed QP structure, as we already discussed in details, compared to HEVC, provides a coding gain of only about 1% for encoding 4K resolution video sequences. And if we take a look at the encoding speed of AV1 in this case is faster than that of VVC, but slower than that of EVC. Okay, now let's take a look at the low resolution videos in different classes. So you can see that actually the coding gains are generally lower. Okay, and if we take a look at the AV1 results, we see that AV1 has quite large overhead of up to 30% for class D low resolution video sequences. Regarding class F, which represents the screen content video sequences, it's interesting to note that VVC provides very significant coding gain, and this is quite impressive, I would say. On the other hand, AV1 has actually significant overhead of about 14%. So the overall average coding gains are about 36% for VVC, about 22% for EVC, and in case of AV1, the overall overhead for this video sequences is about 16%. And regarding the runtimes, VVC runtime is actually the largest. It's a factor of 10 compared to that of HEVC. Similarly, EVC has a runtime of a factor of about 5, and AV1 has a runtime of a factor of about 6. This table summarizes experimental results presented in the previous slide with regard to encoding 4K video sequences, which I believe is the most interesting to show. So let's take a look. On average, VVC outperforms HEVC by about 41%, as we discussed in the previous slide in detail. Similarly, EVC outperforms HEVC by about 29% up to 30%. On the other hand, EV1 outperforms HEVC only by about 1%, while VVC has a coding gain of about 39, as you can see here, compared to EV1, and EVC has a coding gain of about 26 compared to EV1. So this table is a quite nice representation of coding gains for encoding 4K resolution video sequences. I would like to emphasize again that the results presented here are in terms of BDBR, weighted PSNR WAV values, and the results for AV1 presented in this table are in the configuration with fixed QP structure. And now, regarding the experimental results with the AV1 tested in a VBR mode with a two-pass rate control, as you can see here in the last column. So the result presented in the last column is the only difference between this slide and the previous one. So in case of VBR mode, AV1 coding gain compared to that of HEVC is about 20% for encoding 4K resolution video sequences. So it's larger than the AV1 coding gain in case of fixed QP structure. Regarding the encoding time, so AV1 runtime compared to that of HEVC is about 3.5 times larger, and it's actually lower than both VTM and ETM reference software runtime, as you can see here in this table. Regarding the coding gains for low resolution, so AV1 coding gains in this case are also lower than coding gains for larger resolution, which is 4K. If we look at the class F video sequences, which represents screen content, as we already discussed, SV1 coding gain is around 16.5% over HEVC, and its computation complexity is relatively low, and also when compared to VVC computation complexity for encoding class F video sequences. Regarding the average coding gain, it's around 17.5% for all tested sequences, while the runtime is around 3.5 times over HEVC. So this slide summarizes a previous slide for encoding 4K video sequences. The difference between this summary and the previous one is in the AV1 results, which are provided in this table for encoding in VBR mode with two-pass rate control enabled. Now let's take a look at the result. So as we discussed, the coding gain of AV1 over HEVC is about 20%, as we have seen before, and the coding gain of VVC over AV1 is 24% more or less, while the coding gain of EVC over AV1 is around 10%. Great, so let's summarize this presentation and let's take a look at the main key points which we discussed in details. So VVC provides the most significant bitrate savings of around 40% for encoding 4K resolution videos, but also introduces the largest complexity increase. Now, regarding EVC, it provides bitrate savings of around 30% for encoding 4K resolution videos, and the encoding process is approximately twice faster than that of VTM reference software. On the other hand, AV1 with a fixed QP structure compared to HEVC provides bitrate savings of around 1% only for encoding 4K video sequences, and the increase in encoding runtime is about a factor of 4.7. When compared to the computation complexity of EVC in terms of runtime, it actually runs slower. Now, regarding VVC compared to AV1, with a fixed QP structure, the bitrate savings are around 39%, while the encoding runtime is a factor of about 2. And similarly, in case of EVC compared to AV1, the bitrate savings are around 26% for encoding 4K resolution videos, with a computation complexity decrease of around 1.3 times. Finally, AV1 in the 2-pass rate control mode provide bitrate savings of around 20% over HEVC for encoding 4K resolution videos, with a runtime increase of a factor about 3.6 compared to that of HEVC. This slide presents a literature review and it concludes my presentation for today. Thank you.